Hi, and welcome to this next video in a series of exponentials and logarithms. And in this video, this is a biggie. We're going to introduce you to a brand new number, a kind of magical mathematical number that just opens up a whole world of crazy mathematics. And what I'm talking about here is it's something called the base of the natural logarithm. What we get is this value, and it's called e, which is kind of this crazy number that allows us to do all kinds of wicked stuff. It's kind of like, I don't know, like kind of the logarithm version of pi, if you will. You know, kind of pi is just essentially a very simple idea. It's the ratio of the diameter to the circumference of a circle, but it comes up in so many other areas of mathematics. Likewise with e. I'm going to show you where it comes from. There's lots of different ways of kind of getting to this thing, and then we'll have a look at how we're going to use it. So here we go. Right, as well as being a maths teacher, I clearly own a bank as well, and in my bank I'm going to give you a range of possible options for your investments. So we've got 5 options there. For your interest, we're going to either give you one payment each year, and it's going to be 100% interest rate, which is fairly stunning. Alternatively, I'm going to take that 100% and chop it over the course of the year into 2 equal payments, or 4 equal payments to 25, and so on and so forth. So you've got to decide, as an investor in my bank, which one you think is going to be the best. And it might be you're going to go, well, you know, obviously I'm going to take my 100% happy days. Or you might be looking at thinking, well, they're all giving me 100%. What's going on? Well, let's have a little look. So here we go. So our first option, at the end of the year, I'm going to have £2 because there was the £1 that you invested originally, and then the 100% interest I'm going to give you, which is another £1, so you've now got £2. So now let's have a look at option 2, £2 50%. So you've got your original, I'm just going to go to some scribbling, you've got your original £1. I'm going to increase that by 50%, 1.5. I'm going to do that twice. So we've got that. So what you end up with is £2.25. Okay, so now that seems like that's a little bit better. Okay, let's go for the 4 payments of 25%. You can probably see where this is going, but I'm going to scribble it anyway. 1 times 1.25, and that's the power of 4. Bash that into a calculator, and we're getting £2.44. So it's looking like the more of these payments we do, the better our investment is going to get. So let's just have a quick look at that 25%, a slightly different way, that calculation there. So let's say I've got my original £1. I'm going to give you my 100%, so kind of the original amount back, and then I'm going to give you that extra 100%. But that 100% is being chopped into 4 different parts. Now 100% as a fraction would be 1 whole, and I'm going to divide that into 4 equal bits. So there's the kind of the 0.25, and then I'm doing that to the power 4. So if I wanted my payment of 5 payments of 25%, I'd have my original £1, and I'd be times that by, there's the original £1 that you're getting back, plus the 100% interest I'm going to give you, divided into 5 equal payments. And there we go. So that's kind of the same as multiplying by 1.2 to the power 5. Now, I've kind of been a bit laborious over that one just because it's simple enough to see on this slide, but as you'll see later on, you kind of lose track a little bit of where these numbers are coming from. So that's what's going on. So that's now £2.48. And then the 10 payments of 10%, £2.59. So these things are still going up, but the increases we had at the start, it was 25 extra p there, slightly less there. Obviously we're going from 4 payments to 5 and a little bit there, but you know, we're not getting such massive increases as we did right at the start with this. But you know what? It's still no money. So hopefully, you know, you might say, well, let's just extend this principle further, and let's go for, let's say, compound interest, daily interest, or even hourly. So if I did it daily, I'm going to take that 1%, 100%, and I'm going to divide it into 365 equal bits, and then pay it 365 times. So my multiplier becomes that value there. So the amount you'd be getting would be effectively £2.71. Alright, so again, looking good. But again, if we said, okay, rather than daily, let's do that hourly. So let's put an extra 24 payments per day into that. So we're now looking at that. So we're now looking at something to a power that's going to be a very hefty looking number. And what's that going to give us? Well, if you put that in your calculator, you've got 2.718. And now you can see this thing, as we get bigger and bigger numbers, more and more payments, it's starting to settle down a bit, and you can probably sense where I'm going with this one. It will settle down. Let's go every minute. So we've got that calculation, and you can see now we've got 2.714 here, 2.718. The 2.718 is there again, but it's at that point it's slightly different. But if we go again, And now we can see we've got that number there, and these two numbers are looking very, very similar. And so if you kind of put that into your calculator, you'll find on your calculator, you'll find on top of the LN button, you'll find E. Let's say it's a button that looks, let's just scribble it. It's a button that looks like E, and then you've got a box up there. And so if you do that, if you do e to the power 1, what you'll get, if you put that into your calculator, is a value that is 2.718281828, and it goes on and on and on. And that is our value for e. Okay, that is what's called the base of the natural logarithm. And it's that value there. And it's a number, it's irrational, similar to pi, and it does magical things similar to pi does. So let's just have a look at what crazy magical things it actually does and how we're going to be able to use it. The biggest bonus it has for me is the fact that it allows us to do some differentiating of these functions. What we're going to do is extend your knowledge of differentiation now, because up till now you've been able to take something, for example, y equals x squared, and you know dy dx. Bring the power to the front, knock one off the power, you get that. But that doesn't work if we're doing something like that. Okay, as we're going to see, we're going to have issues with that kind of thing. And E is going to massively help us out with that. So let's just have a look at what's going on if we try now to find the gradient of an exponential function. So let's do it from first principles first of all. There we go, there's my diagram. So we've got my original point, if the x coordinate is x, the y coordinate will be a to the power of x. If I move along my curve a little bit, my x coordinate is now x plus that little bit extra, so x plus h, and my y coordinate will be a to the power of x plus h. And differentiating from first principle is basically rise over run. If you remember that structure, so we've got on the top the rise, this is the y coordinate, a to the power of x plus h, minus the y coordinate there, and on the bottom we've just got essentially the distance here between x and x plus h, which will just be h. So that's what we've got. We've got to try and tidy that up a little bit, and the tidying up we can do is going to be here. Using our index laws, we can write that as two separate things. Now you can see we've got an a to the power of x here and a to the power of x there, so we can do a bit of factorising. So let's take that out, and we get that. And now what I'm going to do is write that slightly differently. I'm going to take this section here and just write that as a separate fraction. You'll notice that what we've got is, within my gradient function, my original function was y equals a to the power of x, and my gradient function, that a to the power of x is still there, but it's been multiplied by this thing here. Now, this thing here is just going to be some constant function that is independent of x. That thing is going to just kind of tend, as you make x increasingly small, it will tend to particular values, and the values it will tend to will change depending on how big you choose your value for a. I'm going to have a look at that next. Because what's happening is, let's see, if we have a look at y equals a to the power x, there's our original function, there's our extra multiplier bit that's going to be a constant value, and that thing there is essentially a scale factor that's just going to stretch our function if you think back to your transformation of functions. Now, I'd advise you, if you just want to grab your calculator, and if you pick h as being a very, very small number, for example, like say maybe 1/1,000,000th, and put it in, what you find is your calculator will spit out this number here, 0.69. And so what you've got is my value, my function here, the solid one, is y equals 2 to the power of x, and here's my gradient function, which is 2 to the power of x multiplied by this 0.69 value, so it's kind of shrunk it down in the y direction, and you get something that the gradient function that's exactly the same shape, but below the original curve. And don't worry, I am getting to a point, it is coming surely, do not worry. If we did that with a equals 3, we get a similar thing, but now the value of this constant is actually just a little bit bigger than 1. So it's what it's doing is stretching it up, almost looks like it's stretching upwards in the y direction. Now, as you can well imagine, this kind of constant having to mess around with these constant values which chuck out these kind of great big horrible decimal numbers is a bit of a pain in the bum. So wouldn't it be really, really nice if we could have some function such that our constant value was actually equal to 1? And the reason that would be much, much simpler is that then we'd have, for that particular value of a, whatever a was going to be, that the gradient function would be exactly the same, because the multiplier bit, let's say, is just a value of 1. So what you would have is the gradient function sitting right on top of the original function, and life becomes nice and simple. And you can see that what we had previously, if you remember from the previous slide, we had when a equals 2, and the value was like 0.69. So it was just below, the gradient function was just below our curve. When a equals 3, it's 1.09, so the gradient function is just above it. You can probably guess where I'm going with this one. If a is going to be between 2 and 3, what we're going to get is that value there. That's the one that puts it right slap bang on top of itself again. So what we get is, if y equals e to the power of x, differentiate it, you would get y equals e to the power of x times by that constant value. And up here, in this constant value, for 2tx it was that, for 3tx it was that. For e to the power of x, that constant number is just 1. So you get a differentiation, or a function value, sorry, a function curve that looks exactly like that. And those two things are just one and the same thing. And that is going to make all our calculations and all our differentiation, all our work with these exponential models so much easier. Right, so there we go. That's what we've worked our way up towards. If y equals e to the power of x, where that value of e is 2.718, blah, 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 and that's how you're going to spend all your time working now with e's rather than that big decimal number. If y equals e to the x, then dy dx is also e to the power of x. What you also get is, if y is e to the power of kx, so for example e to the power of 2x, then you end up with that as a rule. Now, for now, you're just going to have to kind of take that one on trust. What you get is the power comes to the front. So that's kind of similar to what we've seen before with differentiation, but notice you are no longer getting the power, taking one off the power. The power stays exactly the same. And like I say, you'll have to take that on trust for now, because there is a reason for that. We'll be able to show the reason for that, but it requires some mathematics that we haven't currently got, but you will absolutely be meeting that next year, and you'll see why this is happening. But the key thing to remember with this one is, yes, the power comes to the front, but your power itself is staying the same. You are not taking one off the power anymore. So just be a bit careful with that one. So let's have a look at some examples. So here we go. We've got some function y equals 4 e to the power 2x, and we've got to find the gradient function. We've got to differentiate it. So what we're going to do is bring the power to the front, but leave the power the same. So hopefully you can see that's just going to become 8e to the power of 2x. The next one, we're going to do it by differentiating the two bits separately. So let's deal with the 3e to the power of x first of all. What's going to happen now is that's going to stay exactly the same. The constant doesn't get affected. It's, for example, the 4 is still in here with the 8. So differentiate e to the power of x, you just get e to the power of x. On this term here, we're going to bring that minus half to the front. So that's going to become minus 4 times minus half, it's going to become plus 2. Power stays the same. So there we go. The third one, we've got a bit of fiddling around to do with the bracket first of all, so we can get into a form we can differentiate. So let's do that. So don't worry, it's not just y equals 2. What I've done is just done the first bit here. So we've got e to the power of minus x times by e to the power of x. When we're multiplying, add the powers. Let's just do a little bit of scribbling there. So we've got, I'm going to do it up here, e to the minus x times by e to the power of x is going to be e to the power of minus x plus x. That's e to the power of 0, which is just 1. So that first term becomes 2. And the second term, we've got e to the minus x, e to the 4x. So that's going to become e to the power 3x. And so now we've done that working out, we can just do the differentiating. Again, we've got a constant term at the front here, so that's just going to disappear. So all I've got to worry about is differentiating that bit there. So what I end up with is dy dx equals minus 9 e to the power 3x. And there we go, there's our differentiating all sorted. Right, final bit just to finish off with is just to say kind of this figure is what you're going to spend all your time working with next year. Load of practical applications. The only other thing I need to mention at this point in time is if you've got a logarithm, and normally we write our logs with a base, so logs the base e of x, what we do is change that slightly. I mentioned it previous because you've got what you've got is this ln button that's on your calculator where you find your e to the power of x button. So logs the base e is just written as ln, and that ln is known as the natural logarithm. So, for example, if we had e squared equals x, then ln x equals 2. Okay, so that's just our basic writing things in exponential form over here, writing things in logarithmic form over here. So if we had an equation to solve, let's go about this the same way as we'd solve all our log equations. So we'll go, let's do a divide by 3 to begin with. Then let's rewrite that using our log laws. So we've got log to the base e of 28 over 3. That's ln 28 over 3 equals 1 minus 2x. And now just solve by moving the 1 over and then divided by minus 2. So we end up with that. Bang that into the calculator using the ln button. And we get our answer x is minus 0.617. So again, that last slide there is just about, it's exactly the same as we've seen before with any other logs, but we're now just using this base e. And let's say you've got your ln button on your calculator to help with that. And by default setting, the vast majority of things that you're going to be working with next year particularly will be in terms of ln, or this thing, the natural logarithm. And there we go. Welcome to a brave new world. And let's say most of this is preparatory stuff for next year. Where you'll see this thing just going crazy with all kinds of differentiation, integrations, trig, and all manner of stuff.